This is a quick lesson that shows that functions of independent random variables are independent. So the topics here are maybe a little bit advanced and you don't really need to know the details, but to make the lesson complete, I go ahead and show that the functions of independent random variables are independent by starting with the definition of a pullback function. So if f goes from r to r as a function, as you're probably aware from your algebra class, the inverse of f may not be a function. So if f of x is x squared, then both 1 and negative 1 map to 1. So the inverse of f is not a function, which is square root x, because you'll have two branches, right? You have square root x and negative square root x. But we can define a function on the power sets, or from one set to another set. So the inverse of a set A is all the x in R such that f of x lands in A. And that's the pullback function of f. So if f of x was x squared, then f inverse of the set 4 is negative 2 and 2. And f inverse of the interval negative infinity to 0 is the empty set. And the point is here is that the pullback function takes in a set and gives you out back a set, and that is a function. So if f and g are functions and x and y are independent random variables, so we have two independent random variables and functions of them, f of x and g of y are independent random variables. A couple of examples, I guess I have some below. So if x and y are independent, then e to the x and e to the y are independent, because e to the x and e to the y are functions of x and y. Also, I could take f of x equals x, so I could get x, and g of y equals y squared, so x and y squared are also independent. And to show this, I'm going to leave this window up here because that was in a good place. We're going to take two sets A and B of R, and remember that the random variables are independent if the probability that they're in those sets is the product of the probabilities that each random variable is in those sets. So we're looking at the probability that f of x is in A and g of y is in B, but this is the probability that x is in the pullback of A and y is in the pullback of B. Because in order for f of x to be in A, that means that x has to be in some value that maps to A. And also for g of y to be in B, that means that y was some value that g maps to B. And since x and y are independent, no matter what these two sets are, by independence, this equals the product that x is in f inverse of A and y is in g inverse of B. And this is the same as the probability that f of x is in A and that g of y is in B, showing that f of x and g of y are independent by definition.